Hey everyone. In the last episode, we introduced the concept of a random variable, the central notion of probability. To recall, whenever the true result of our experiment is a number, we're dealing with a random variable. A random variable, let's call it capital X, assigns a number to each outcome of the experiment. So we can view X as a real valued function on the sample space. It takes an input from the sample space, which is an outcome, and outputs a number. For example, if we flip 3 coins, then the number of heads is a random variable. There are 8 possible outcomes, all tails, 2 tails, and then a head, and so on. The set of all outcomes forms the sample space, and the random variable X assigns the number of heads to each outcome. For example, if you flip all tails, then the number of heads is 0, and if you flip TTH, then the number of heads is 1, and so on. Another example. If you ask a random person on the street, how old are you? The age is a random variable. Here, the sample space, all possible outcomes, are all the possible people that you can meet, and the random variable X assigns each person his or her age. Another example. Let's look at the number of children in a randomly chosen family. The sample space, the set of all outcomes, is all the families that we can potentially ask, and the random variable X assigns every family the number of children in that family. When we have a random variable, what is the first question we may ask? It is, what values does it take and with what probabilities? How many children are possible? And what are the probabilities that the family has no children, 1 child, 2 children, and so on and so forth? The knowledge of values and their probabilities is called the distribution of a random variable X. If the random variable is discrete, which means that it can take on finitely many values, or possibly countably many, then we can explicitly write down the list of these values and their probabilities. This is called the probability mass function, or PMF. It answers the question, what is the probability that the random variable X takes this specific value, little x? The full notation here should be like this. We're looking at the event, so we're including all the outcomes for which the random variable as a function takes value little x. But from now on, we will skip the little s from the notation, writing it like this. So the probability mass function captures the distribution of x. For instance, in this example, P of 0 is the probability that the random variable x takes value 0. It only happens in 1 outcome out of 8 outcomes. So the probability is 1 over 8. Next, P of 1, there are 3 outcomes on which random variable takes value 1. So the probability is 3 over 8, and so on. That was what we did in the last episode. Random variable usually takes on many values. Number of children, age, this. But there is a single value that best describes the random variable. It is what we expect the number of children to be in a randomly chosen family, or what we expect the age of a randomly chosen person to be. So today we will mathematically introduce the concept of expected value or expectation, which is more colloquially called the average or the mean of a random variable X. We will in fact write down the formula to compute the expected value. And let's do it on a specific example first. Suppose we're doing a study of 836 families. Suppose when we ask these families, 502 of them have no children. 140 had 1 child, 127 families have 2 children, and 67 families have 3 children. What is the average number of children in a family from this group? We can compute it by dividing the total number of children by the total number of families. The total number of families is 836, and to compute the total number of children, there are 502 families with no children, 140 families contribute 1 child, 127 families contribute 2 children each, and 67 families contribute 3 children each. And when we compute the ratio, it happens to be 0.69. And now let's express the same solution probabilistically, where the experiment is to choose a family at random, uniformly, so any family is equally likely. And the random variable x is the number of children in a randomly chosen family. What is the distribution of x? What values does it take and in what probabilities? In other words, what's the probability mass function of x? P of 0, which by definition is the probability that x equals 0, the probability that when you choose a random family from this group, it will have no children. There are 502 families like this out of 836. P of 1 is the probability that x equals 1, which is the probability that a randomly chosen family from this group is a family that has 1 child. There are 140 families like this over 836. Similarly, P of 2 is 127 over 836, and P of 3 is 67 over 836. Now, if you look at the previous solution, this ratio appears there. And this ratio also appears there. And this. And this. So we can rewrite this formula for the average as 0 times this ratio plus 1 times this ratio plus 2 times this ratio plus 3 times this ratio. And that's what we may call the expected value of x, our expectation of the number of children when you choose a family at random. This formula can be applied in any situation, and we can take it as a general definition of expectation. We define the expected value of any discrete random variable x and denote it by E of x as a sum over all values that x can potentially take, and in the sum we multiply each value by the probability that x takes this value. So it's x times probability that x takes this value, or in terms of PMF, just like we wrote here, we sum over all possible values xi times the probability that x takes that value. This is a general definition of the expected value of a discrete random variable x. Let's make this definition a little more friendly, more intuitive. For example, suppose a random variable x takes capital N values and all of them are equally likely, which, by the way, does not happen here. These probabilities are different. But if they were the same, then all these probabilities would be 1 over n. And that's because the total sum of these probabilities needs to be 1, and there are capital N of them. In this case, P of xi is 1 over n, so we can pull it out of the sum, and the expected value becomes this. This is just the arithmetic mean, the true average of capital N numbers. So if random variable x takes these values and all of them are equally likely, what's the expected value? Just take the arithmetic mean of them. But in general, that doesn't happen. The probabilities need not to be the same. Then we can look at P of xi's as weights. So this becomes a weighted sum. It gives more weight to the more likely values. Also, if you remember physics, you may recognize this as the center of mass of the particles xi with masses P of xi. So the expected value, which in probability corresponds to the notion of the center of a random variable, if you will, corresponds to the physical notion of the center of mass. And now let's practice with a couple of examples. In the first example, a random variable x is the number of heads in 3 coin flips. Let's compute its expectation. We introduced this random variable here. We computed its probability mass function here. So let me copy it. And let's compute the expected value from this formula. It is the sum, and in the sum, we multiply each value by the probability that the random variable takes that value. So it's 0 p of 0, 1 times p of 1, plus 2 times p of 2, 3 p of 3. And if we substitute these values, we get 1.5. This should be intuitively clear. What's the expected number of heads in 3 coin flips? Well, half of the coin flips usually come up heads, and half of 3 is 1.5. It makes sense. And now we're ready for a fun example where we analyze a lottery, specifically a 6 out of 49 lottery. There are 49 numbers total. To play the lottery, we choose 6 from these numbers in any order. If we choose all 6 correctly, we win the grand prize of $1,200,000. If we choose just 5 correctly, then we win a minor prize of $800. If we choose 4 correctly, then our prize is just $35. And if we choose 3 or less correctly, then we get no prize. Let's compute our expected winnings, the expected sum of money that we win in this game. So our random variable x will be our winnings. And to compute the expected value of x, we need first to compute the distribution of x, or the probability mass function of x. X is a discrete random variable. It can only take these 4 values. And let's compute each of these probabilities. What's the probability that x takes this value? That is the probability that we guess all 6 numbers correctly. A picture could help here. Here are all 49 numbers, of which only 6 are correct, and 43 are incorrect. The probability that we guess all 6 correct. On the bottom, we put all the ways we can play this lottery. On the top, we put all the winning ways. There is only one winning way to guess all 6 numbers correctly. And how many ways are there to play this lottery? We just need to write down any 6 numbers out of 49. And that's 49, choose 6. Next, let's compute the probability that x takes value 800, which is the probability to choose 5 correct and 1 incorrect number. Again, it is a ratio. On the bottom, there are all the ways to play this lottery. And on the top, there are all the winning ways. The ways to choose 5 numbers correctly and 1 incorrectly. To do that, we need to choose 5 numbers from here and 1 number from here. So 6 choose 5 times 43 choose 1, because of the multiplication principle. For any choice of the correct numbers, there's this many choices of the incorrect numbers. So we get 6 choose 5, 43 choose 1. Similarly, the probability that x takes values 35 is the probability to choose 4 numbers correctly and 2 incorrectly. On the bottom, there are all the ways to play this lottery. On the top, there are the number of ways to choose 4 numbers from the pool of correct numbers and 2 numbers from the pool of the incorrect numbers. And that's 6 choose 4 times 43 choose 2. Computing P of 0 may look tricky because there are so many scenarios: 0 correctly, 1 correctly, 2 correctly, 3 correctly. But there are 2 ways to get around it. To just realize that P of 0 is the complement of anything else. The probability to get no prize is 1 minus the probability to get the prize. And the probability to get some prize we have already computed. It's the sum of these. And now we can compute the expected value. It's a sum of the values that the random variable can possibly take times the probability that x takes these values. 1,200,000 times probability of that plus 800 times probability of that plus 35 times probability of that plus 0 times probability of 0. Now, because of this 0, this term does not contribute anything, so we can just skip it. And so this is the second way to deal with this, is not to compute P of 0 at all, because it will not be used in the formula anyway. Now, if we substitute each of these numbers, this for this, this for this, this for this, the calculation gives 0.13 or 13 cents. So the answer is that the expected winning in this lottery is just 13 cents. Disappointing, isn't it? The fair price to pay for the lottery ticket would be 13 cents. Then you will be even. Next time, we'll cover more cool examples related to expected value. Stay with me and have fun.